In this video, we're going to think about how we can evaluate the expression 0 to the power of 0. What's its numerical value? There are a few strings of logic that lead to different answers, but which one is right? First, let's just recap what we mean by this power or exponent notation. For example, 3 to the power of 2 means that we write down two 3's on the page and multiply them together. 3 squared is equal to 3 times 3, which is equal to 9. The 3 in this case is called the base, and the 2 is called the exponent. 5 to the power of 4, or 5 with an exponent of 4, means that we write down 4 5's on the page and multiply them all together. 5 to the power of 4 is equal to 5 times 5 times 5 times 5, which is equal to 625. And we can generalise that. X to the power of y means we write down y x's on the page and multiply them all together. Great, so 0 to the power of 0 just means that we write down 0 times and multiply them together. Oh dear, what does that even mean? Well, we could argue that whenever we multiply something by 0, the answer is 0. So however you define 0 to the power of 0, it's going to involve multiplying by 0, and therefore the answer should be 0. 0 to the power of 0 equals 0. Well, that seems logical at first sight, but if we're writing down 0 times to multiply, then we're not actually multiplying anything by 0 because there are 0 of them to multiply. Perhaps we could try to plot a graph of y equals 0 to the power of x and see if there's a logical value for y when x equals 0. Well, it looks like we've got a straight line, and if we extrapolate that back to x equals 0, it looks like we've got y equals 0 at that point. But that doesn't prove anything though. There are plenty of functions that do something different for a particular x value. For example, y equals 1 over x. In this case, it looks like the value of 1 over x is approaching positive infinity as x gets closer and closer to 0. So we might be tempted to suggest that 1 over 0 is positive infinity. But wait! Approaching x equals 0 from the negative direction, we see the values of 1 over x getting more and more negative, approaching negative infinity as x gets closer to 0. So is the value of 1 over 0 equal to positive infinity or negative infinity? Well, mathematicians say neither. They say 1 over 0 is undefined. We need to get back to our graph of y equals 0 to the power of x and try out some negative values. First though, let's just recap what we mean by x to the power of y when y is negative. Do we mean that we write out x a negative number of times and multiply them together? Well, how could we even do that? In fact, there's a mathematical convention that turns out to have some other useful applications with exponents. Let's start with 3 to the power of 4, then think about 3 to the power of 3, 3 to the power of 2, and 3 to the power of 1. As we increase the exponent by 1 each time, we're multiplying the value of the expression by another 3. 3 to the power of 1 is 3, we then add 1 to the exponent to get 3 to the power of 2, and multiply the expression by 3 to get 3 times 3 equals 9, so 3 to the power of 2 is 9. And so on. When we add 1 to the exponent, we multiply the value of the expression by the base. And the other way, as we reduce the exponent by 1 each time, we're dividing the value of the expression by 3, the base. Now, if we carry on applying that rule, then 3 to the power of 1 is 3, and 3 divided by 3 is 1, which is 3 to the power of 0. 3 to the power of 0 is 1 because it means 3 divided by 3, which gives us the result of 1. Well, under that convention, 0 to the power of 0 means 0 divided by 0, which is undefined. But let's carry on with our line of thinking using 3 as a base. So 3 to the power of 0 is 1. Let's subtract 1 from the exponent again and divide the value of the expression by 3 again. 3 to the power of 0 is 1, and 1 divided by 3 is a third. Then subtracting 1 from the exponent gives us 3 to the power of negative 1. And if 3 to the power of negative 1 is a third divided by 3 is a ninth. So 3 to the power of negative 2 is a ninth. And 3 to the power of negative 3 is 1 over 27, and so on. Now we can see a pattern. 3 to the power of 1 is 3, and 3 to the power of negative 1 is 1 over 3. 3 to the power of 2 is 9, and 3 to the power of negative 2 is 1 over 9. 3 to the power of 3 is 27, and 3 to the power of negative 3 is 1 over 27, and so on. So in general, x to the negative y is equal to 1 over x to the power of y. And this convention is useful and consistent with the rest of the logic around exponents. Now we can get back to thinking about our tables of values of 0 with negative exponents. We saw that y is 0 for positive values of x, but oh dear, 0 to the power of x is undefined for all negative values of x. That doesn't help in our quest to find out how to evaluate 0 to the power of 0. If we approach 0 to the power of 0 with smaller and smaller positive exponents, 0 to the power of 3, 0 to the power of 2, 0 to the power of 1, then it looks like 0 to the power of 0 should be 0. But if we approach it with negative exponents, closer and closer to 0, 0 to the power of negative 3, 0 to the power of negative 2, 0 to the power of negative 1, and so on, then they're all undefined. It doesn't seem obvious whether 0 to the power of 0 should be undefined or not, because 0 isn't a negative exponent, but from this direction it doesn't look like 0 to the power of 0 should be equal to 0. Okay, let's try another approach. Let's look at y equals x to the power of 0. As we just saw, 9 to the power of 1 is 9, so reducing the exponent by 1 means that we divide the value of the expression by the base, 9 in this case, and 9 divided by 9 is 1, so 9 to the power of 0 is 1. Similarly, 6 to the power of 0 is 1. 3 to the power of 0, 1, and it looks like 0 to the power of 0 ought to be 1 as well. And if we have a look at negative exponents, again, negative 9 to the 1 must be just negative 9. So reducing the exponent by 1 to 0, we must divide the expression by negative 9. And negative 9 divided by negative 9 is equal to 1. So negative 9 to the power of 0 is 1. Likewise, negative 6 to the power of 0 is 1, negative 3 to the power of 0 is 1, and so on. Well, this looks pretty convincing. Thinking about y equals x to the power of 0, when x is negative as it approaches 0, x to the power of 0 is consistently 1. As x is positive and approaching 0, it's also consistently 1. Surely 0 to the power of 0 must also be 1. The thing is, having a value close to 0 isn't the same as having a value of exactly 0, so we haven't proved anything. It's a bit like a raffle, in which each of 10 people gets a ticket with a number from 1 to 10 on it. Then a number in that range is chosen at random, and the holder of the ticket with that number wins a fabulous prize. Let's say that ticket number 5 is the winner. Using the logic that we used with y equals x to the power of 0, we could say that ticket numbers 1, 2, and 3, and 4 are all losing tickets, and tickets 10, 9, 8, 7 and 6 are 2. So whichever way you approach ticket number 5, you're getting losers, so ticket number 5 must also be a loser. We've overlooked the fact that there's something unique and spectacularly different about ticket number 5. It's the winner. So we've come up with 3 possibilities for the value of 0 to the power of 0. It could be 0, or undefined, or 1, but there doesn't seem to be a consistent and entirely logical killer argument for it to be any one of those in particular. Well, it turns out that for mathematicians, it's most useful if we define 0 to the power of 0 as being equal to 1. So that's what we've done. There isn't an answer that you can prove, but choosing to use a value of 1 for the expression 0 to the power of 0 doesn't break any other rules, and it's convenient. Sometimes we define things that seem to make sense, and sometimes we use logic and build provable theorems from our definitions. This is one of those occasions where we've just made a group decision to define something in a certain way because it looks useful. A reasonable simple example of this sort of thing is when we define a straight line as being the shortest one-dimensional path between 2 points. Technically, it then extends infinitely beyond the 2 points in either direction. Now we can pick a point on the line and define the angle measure from the line in one direction to the line in the other direction around that point as being 180 degrees. We can now derive and prove a number of rules using straight lines. For example, when 2 lines intersect at a point, then vertically opposite angles must be equal. Then, if we introduce a parallel line, another definition, we can call these angles alternate angles and prove that they must be equal in measure. We can then define a polygon as a 2-dimensional plane enclosed shape with 3 or more straight edges, and then a triangle as a polygon with specifically 3 edges. Now we can use the definitions and proofs we have so far to prove that the sum of the interior angles in a triangle is 180 degrees. Some parts of mathematics are definitions, and some are logical developments of those definitions. Back to our 0 to the power of 0 definition then. There's a thing called binomial theorem, which amongst other things helps us to quickly multiply out expressions like a plus b all to the power of n. For example, to expand x plus 3 all to the power of 6 takes quite a lot of working out if you do it longhand, but you can more or less write it straight down if you know the binomial theorem. Now, if we had an expression like 0 plus x all to the power of 6, then clearly 0 plus x is just x, so this is just x to the power of 6. And the binomial expansion of that would be this. and 0 to the power of 1, 0 to the power of 2, and so on are all 0, so these terms are all multiplied by 0 and become 0. But if 0 to the power of 0 was also 0, then that first term here would become 0 too, and we'd be saying that 0 plus x all to the power of 6 is equal to 0, and that just wouldn't be right. It's much easier to define 0 to the power of 0 as being equal to 1, and then this works just fine. Now, there are other ways around this problem, and this isn't the only reason for choosing to define 0 to the power of 0 as being equal to 1, but it is an example. The whole of mathematics starts with seemingly sensible definitions, known as axioms, and from these the rest of mathematics is built. One of the things that's been agreed along the way is that it will be useful if 0 to the power of 0 was defined as being equal to 1. When you subscribe to our channel, remember to click the bell to ensure you get notifications about our new videos. And for more mathematics content, why not follow the link in the description below to nagwa.com.